Welcome to The Explainer. We've got an incredible piece of new research today, and honestly, we're treating it like a breaking news story because, well, it absolutely is one. The paper is called Astrometric Microlensing Probes of the Isolated Neutron Star Population with Roman. It's led by Zofia Kaczmarek and her colleagues, and it's published in the journal Astronomy and Astrophysics in 2026. Basically, this sets the stage for a spectacular hunt for some of the universe's most extreme, and literally its most hidden objects. So let's dive right in. So how exactly do you find a ghost in the vastness of space? You know, neutron stars are the crushed, ultra-dense cores of dead stars. They hold the secrets to the most extreme physics in the universe. We're talking environments so intensely pressurized that matter behaves in ways we literally can't even replicate here on Earth. But here's the catch. Isolated neutron stars are completely invisible. They don't emit any light of their own. They're essentially stellar ghosts, just floating completely alone out there in the dark, which makes them, as you can guess, nearly impossible to find. And because we can't see them, well, we can't weigh them. Now, you might be thinking, wait, don't we already know about neutron stars? And yeah, we do. But almost all the neutron stars we've actually managed to weigh are part of binary systems. They're paired up with another star, feeding off of it, or even crashing into it. But that data is super biased. I mean, a star's mass and rotation can completely change when it's actively cannibalizing its neighbor. To really understand how massive stars die, we desperately need to find and weigh the ones traveling completely alone.
And that brings us to our brand new investigative tool. Take a look at the footprint of the upcoming Roman Space Telescope's Galactic Bulge Time Domain Survey. Roman is going to stare deep into the crowded, totally chaotic center of our galaxy. By continuously monitoring hundreds of millions of background stars, it's perfectly positioned to finally spot these invisible ghosts. It does this using a genuinely brilliant trick of gravity called microlensing. You can think of it kind of like a giant cosmic magnifying glass. When a dark, really heavy object, like our invisible neutron star, drifts exactly in front of a distant, bright background star, its intense gravity actually bends the fabric of space around it. This warped space acts as a lens, and it temporarily magnifies the light of the star right behind it. During this whole event, Roman's going to be looking for two very specific clues. The first is photometry. That's when, as the ghost passes by, the background star temporarily gets brighter and then fades out. The second clue is astrometry, where the gravity of the ghost actually makes the background star appear to physically wobble in the sky. By measuring both that flash of brightness and that tiny telltale wobble, we can calculate the exact mass of the invisible object passing in front of it. The simulation, hunting for the fingerprint. Now, space is full of all sorts of dead stars, right? So how do we know a wobble is caused by a neutron star and not, say, a black hole? Well, Kaczmarek and her team built this massive simulation of the Milky Way to figure that out. And an absolutely crucial variable they baked into their simulation is something called a natal kick. See, when a neutron star is born in a highly violent supernova, the explosion acts like a massive rocket engine. It gives the newborn dead star a tremendous velocity boost. We're talking rocketing it through space at up to 450 kilometers per second. The researchers wanted to see exactly how this extreme speed alters the microlensing data. Now, what's really interesting about this slide is the breakthrough they found. Notice that dramatic red circle around the purple dots extending out to the left? In the simulated Roman data, the researchers discovered a totally unique diagonal cluster. They call it a spur. This spur is a signature left solely by fast-moving neutron stars. It stands completely apart from the data clusters of black holes, white dwarfs, or just regular stars. This spur is the smoking gun. Basically, objects that fall into this data spur are nearby, they're moving incredibly fast because of that needle kick we talked about, and they act as perfect mesolenses. That just means they bend light in a way that is highly visible to our instruments. Because they cover so much ground so quickly, they sweep right across our line of sight and leave a distinct, perfectly measurable signature that can literally only belong to an isolated neutron star. Now you're probably asking, how confident are we in this? Well, this is a highly rigorous simulation using incredibly complex models of the Milky Way and the exact technical specs of the Roman telescope. But, to be fair, the researchers are careful to point out that modeling the exact galactic migration of these stars over millions of years, it's extremely complex. Actually, scratch that, it's mind-bogglingly complex. It's a brilliant roadmap for sure, but the ultimate test really comes when Roman actually launches and starts collecting real light. So the crucial point is the incredible yield we're actually expecting here. Out of roughly 11,000 total microlensing events the simulation predicts Roman will observe, it should find about 100 perfectly measurable, completely isolated neutron stars. 100. To put that into perspective, right now, our catalog of highly confident, directly weighed, isolated neutron stars is, well, it's virtually zero. So finding 100? This is going to be a monumental leap forward. As the paper itself states, this is going to provide an unprecedented census of isolated stellar remnants. But what does this actually mean for the future? Well, unlocking the precise masses of these 100 isolated ghosts will finally let us measure their equation of state. That is essentially the rule book for how matter behaves under the most crushing pressures imaginable. It'll definitively tell us if the mysterious mass gap between the heaviest neutron stars and the lightest black holes is a real thing, or if it's just an illusion caused by our biased binary data. Which leaves us with this final, lingering thought. When Roman launches and we finally weigh the ghosts of the Milky Way, what new physics are they going to reveal? I mean, what hidden phases of matter are locked inside those invisible speeding cores just waiting to be uncovered? The dark universe is about to get a whole lot brighter. Thank you so much for exploring this amazing research with me today.